What will we learn from going back to the moon? Is there dark matter in the solar system? Which telescopes would work best for time delay cosmography? And in Q&A Plus, which planets will be left after the sun dies? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Anne Armstrong, I was wondering if you have an opinion about time delay cosmography. What future telescopes might best suit this new, exciting way to measure time? So this is an approach to try and measure the Hubble constant, which is the expansion rate of the universe. And there are sort of multiple ways that are used to do this. One is that you measure relatively nearby objects using this thing called the distance ladder. So you measure Cepheid variables, you measure type 1a supernovae, and you get one number for the Hubble constant, the expansion rate of the universe. And then the other method is to measure it in the cosmic microwave background radiation. Of course, the fact that the two numbers aren't the same gives you this tension. And another way to sort of think about the Hubble tension is to think about the age of the universe that these numbers give you. So that the expansion rate of the universe, if you just calculate it backwards, then it tells you how long the universe has been expanding. And so when you measure it via, say, Cepheid variables, you get that the universe is 13 billion years old. And when you measure it via the cosmic microwave background radiation, you get that the universe is 13.8 billion years old. And so there's this discrepancy of 800 million years. And this is weird. And it should be the same number, and yet it isn't. So why? So astronomers are trying to develop other methodologies for measuring this expansion rate, and ideally ones that are independent, that don't require the distance ladder. So, so one of these ideas is the concept that you just mentioned, the time domain cosmography. I have a hard time with that. Maybe it's because it's too similar to cosmology. And the gist of this is that you use a strong gravitational lens. And, you're probably familiar with these strong gravitational lenses, or Einstein crosses are one example, where you've got this foreground galaxy cluster, and then you've got some background object like a galaxy. And that galaxy is being lensed. So the light is leaving the background galaxy. It is taking paths, multiple paths around the foreground object. And then you're seeing a bunch of different versions of the same object. And then where this becomes very powerful is that you can have a supernova go off in the background object. And then you see the light appear in the different galaxy lenses at different times. And so that means that the light took a different amount of time to make the journey to be able to show up, right? And it could be off by a matter of months or even a couple of years, which is pretty incredible. So astronomers have figured out how you can use this as an independent way of measuring the Hubble constant, the expansion rate of the universe. And the important thing is that you have to know the mass of the object that is doing the lensing, so the galaxy cluster that is in the way. And if you can work out the mass of the lensing object, and then you can trace the journey then that the light took to be able to come around the lens to take up its position. And from that, you can then calculate, right? One part of the light is taking one amount of time, or, is traveling a certain distance. Another light is traveling another distance. And so this expansion rate of the universe is, because the light has been traveling for potentially billions of years before it even got to the gravitational lens and went around it. And then several more 100 million years to get to your eyes, or to our telescopes. And so that time that it's spent going through intergalactic space is going to be different as it's going around the lens to follow these different journeys. And you can actually calculate the Hubble constant in an independent way. And ideally, eventually, this will become very, very accurate. And you'll be able to have this number that will then be useful to calculate that it's totally independent. There's a bunch of these other sort of ideas about independent ways of measuring the Hubble constant. The one that is most exciting actually is gravitational waves, because all of the other methods are by measuring different aspects of electromagnetic radiation, and gravitational waves are different, and they are independent from radiation. And so essentially, when you measure two black holes spiraling in and merging with each other, you can determine the distance to that collision just by measuring the sort of final moments before they collide. The problem is that the error bars are just way too big, that they are just they're not useful because they're so wide right now. But eventually, if we get better gravitational wave telescopes, we'll be able to measure that as another fourth independent way of measuring the expansion rate of the universe. Eventually, we will solve the Hubble tension. Not many eclipses left. What is the most important long-term information mankind will acquire from creating a permanent presence on the moon? Well, I mean, the most important thing that we will learn is how to live in space. Like that is really the beginning and the end of why we should be sending humans into space. That, if what you want to do is science, you send the robots. If what you want to do is asteroid mining, you send the robots. That the reason we will send humans to the moon, the reason we will send humans to Mars, is because that's how we will learn to live in space. And there's no way to do it but to do it. And there are so many little lessons. When you think about how people have learned to, say, live on the sea, right, where people are sailors, and they have all of these things about reading the weather and fixing their equipment and navigating and then doing their job, whatever their job is, right? If they're fishing or if they're running a cruise ship or whatever, that everything is made that much more difficult on the ocean. And it's the same idea that, once you go to the moon, you have to bring your entire environment with you. There's nothing there's no oxygen, no atmosphere you can breathe. It doesn't rain. Plants aren't growing. You can't go down to the ocean. You can't, go to a river to pick up things. Like, you have to bring everything. You have to recreate the entire Earth ecosystem, or you have to create the entire environment that the human being needs to survive by yourself with your technology. You have to handle generating oxygen, generating water, generating food, dealing with waste, dealing with energy, dealing with materials, repairing stuff, right? Like, there's just like the laundry list, it just goes on and on and on. We think we know at large scale how to do some of this stuff, but we just don't. We have orbital experience, which has taught us a lot about the effects of being in weightlessness on the human body. We developed better methods for toilets and recirculating water systems and oxygen, as well as how to refuel the International Space Station and send it resupply. So we've learned a ton in low Earth orbit, but now we have to take those lessons and extend them out to a place that is farther away and more dangerous, like the moon. And the moon is still baby steps compared to going to a place like Mars. Like, at the moon, you're just a couple of days away from being able to send rescue supplies, from being able to evacuate somebody from a moon base back to Earth. Once you go to Mars, you are on your own. You are looking at months, if not years, for you to be able to bring someone home. What if someone gets appendicitis, right? What if someone has a tooth abscess? What if somebody is pregnant? What if your carbon dioxide scrubber breaks down? Like, these are all the kinds of challenges that we're going to have to figure out. And so let's figure them out close to home before we try to figure it out things farther away. So that's it. Like if they don't do one lick of science, they don't step outside and pick up any rocks, it will still be valuable to send humans to the moon. Now, of course, you get the science as the bonus, right? Like, absolutely do science while you're there. But I don't think we should lose sight of the reason why we're going to a moon base, and that is to learn to live in space. And that from then we can learn to live on an asteroid, and then we can learn to live on Phobos, and then we can learn to live on Mars, and then we can learn to live on other places, right? Maybe in the cloud tops of Venus, and eventually on our giant spinning O'Neill cylinders. And at some point, 300 years from now, we will be a true solar system spanning civilization. It's time to shout out all the new $5 patrons and above. Rich Brooks, Stephen Cook, Alexander Crowther, Michael Johnson, John D. White, Callum Robertson, Marjan Rotting, Robin Sommerstrom, Laser Blazer, and saxsql.com. Join our club at patreon.com/universe today. Jesse Notot. In the case of World War III or any other major conflict, were the satellites to be a target, do you think the space debris could prevent us from going to space? And if yes, for how long? Yeah, so this is a capability that all of the major spacefaring nations have demonstrated. So the Russians, the Americans, the Indians, and the Chinese have all demonstrated that they can launch missiles from an aircraft, and then that missile will fly up into space and take out a satellite. Now, all of the nations have been testing them on their own satellites, but the result is space debris and a sort of disturbing amount of space debris that not only sort of maintains at the orbit that they were at, but actually can fly into higher orbits and can even risk the International Space Station. And then, of course, if you send a lot of debris, like in the case of a war, taking out your enemy's ability to see the battlefield, communicate, get GPS, weather, it's a big goal. And I guarantee that all of the nations know the locations of all of the satellites that they would destroy if it actually went to war. And they have missiles with that satellite's name on it. And yeah, it would be a disaster for the near space environment. You would be causing thousands of pieces of debris for every satellite that you destroy. And so if you're going to destroy hundreds of your enemy's satellites, you're going to create hundreds of thousands of pieces of debris. That debris is going to hit other spacecraft satellites. It's going to cause more debris, and it's going to be a mess. And that is the bad news. Well, I mean, apart from the war, right? Like the war is the bad news, but also we're going to have this mess. But the good news is that this is all in low Earth orbit, and so these satellites are in the 3 to 500, 600 kilometers altitude, and that space debris at that altitude will clean itself up relatively quickly in the 5 to 10 years range. So there would be a time when existing satellites would take an enormous amount of damage. We would see a much higher failure rate, that people would consider the risks of trying to do some space flight, launching humans to space, maybe is going to be too extreme to actually consider it. But then over time, all the debris would be cleaned up, would all re-enter the Earth's atmosphere, and then it would be kind of pristine again. The more worrying thing would be if people actually started to go after their higher satellites, so the ones that are in the, say, 2,000 kilometers altitude, because those can take hundreds or even thousands of years to re-enter the atmosphere. Those are like where weather satellites are, GPS satellites. If you turn those into debris, then there's just no cleaning that up for hundreds, if not thousands of years. And now, it's a much bigger volume of space, but still, it would be a big problem. So yeah, we don't want people to go to war. And if they do go to war, we don't want them to be destroying satellite networks. And if they do, then we want them to limit it to low altitude satellites and not the high ones. As Farron, why does the universe appear to be the same size in every direction? Because what you're seeing is the age of the universe, that light has been traveling for 13.8 billion years since the Big Bang, minus 380,000 years, right? The cosmic microwave background. And it has been traveling that long in all directions to reach you specifically. That, we always talk about this idea of the universe. We talk about the observable universe, and the observable universe is just the amount of the universe that you can see where the light has traveled for 13.8 billion years to arrive at your eyeballs. And I see a different observable universe than you do. And it assumes that the speed of light is constant. The cosmic microwave background radiation has been traveling for 13.8 billion years from all directions to reach you. But yeah, you are seeing your personal observable universe. The actual size and shape of the universe is unknown. Could be infinite, might be finite, could have some weird topological shape that matches the geometry that they measure in the universe, but it is what you are seeing. And so, the analogy that I always use is that you're in fog, right? And so you're standing in fog and you can see your hands very close to you, but far away, things are harder to see. And eventually all you can see is just the fog. And then your friend might be standing beside you. You say, like, why is the sphere of fog around us always the same size? What's that about? Right? Why does the fog appear to be the same size around us right now? Well, because it's how well the light can get to you through fog particles. And that if there was less fog, you would be able to see farther. This is where it kind of falls apart. But it is custom to you that I see a different fogiverse than you do. Gio Hondo, do we know if dark matter is possibly in our solar system? I mean, it all depends on what dark matter is, but it's believed that there is dark matter everywhere. The actual concentration of the dark matter would be very low inside our solar system, like probably on the order of an asteroid, a small asteroid's worth of dark matter or mass worth of dark matter, because dark matter is this giant halo that surrounds the Milky Way galaxy, and it accounts for most of the mass in the Milky Way. But space is very big. And so when you kind of spread that mass out across this entire volume of space, the amount of dark matter that is present in any small area is actually going to be very small. So in the solar system, most of the solar system's mass is not dark matter. It is planets and the sun. But there would be roughly an asteroid's worth of mass in the solar system that is dark matter. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? And we call that Q&A Plus. And this week's bonus question, which planets will be left after the sun dies? I'll put a link in the show notes. All right, those are all the questions that we had this week. Thank everyone who asked your questions into the YouTube comments, everybody who joined me for the live show. Now, we record the live show every Monday. Right now, we're doing them at 5 p.m. Pacific time, so definitely check out. It should be an event here on the channel, but if not, on Monday at 5 Pacific. Now, I'm going to chat about how you can get some astronomy gear for cheap. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylot, Cooper Nelly, Dark Finga, David Gilton, David Matz, Evan Duppro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneStepAnimals.org, Rank Heidi, Richard Williams, Sean Sargent, Team Father Monday, Team 49, Telescopes Canada, Vlad Shiplin, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So I talk a lot about the telescopes that I have. I have a bunch of them here behind me. I have a bunch that have shown up in various videos, sometimes behind me. Sometimes they're out being used. And this is fairly recent. I've had one telescope for the longest time, and now I think I have 6, and I have a pair of binoculars. So getting some of these new telescopes, someone recommended their technique, and I thought it was really smart, which is that you just go to Facebook Marketplace. And people are often selling telescopes on Facebook Marketplace and binoculars. And because people will be really enthusiastic about astronomy as a hobby, and then maybe they won't want to continue using it, they're looking to get rid of it. Or if someone buys it for the kid, the kid goes off to university and no one's using it, they may sell it. That's how I got my 8-inch Dobsonian, was that their kid went off to study astronomy at university, which I think is very cool. Maybe I'll report on their work someday. And so, like, just before recording this episode, I did a quick search on my local Facebook Marketplace, and I don't live in a very big city. We've got about 50,000 people in my city. There was a copy of the 8-inch Dobsonian that I have. Someone is selling for about the same price. They're selling for like 500 Canadian, which is a really good price. Normally it's like 1,100 Canadian new if you bought it. So you should be able to get a telescope from Marketplace for a couple of $100 that's going to do what you need. Try to get a Dobsonian if you can. A 6-inch Dobsonian, even a 4-inch Dobsonian will do well. Some of the telescopes will have a more complicated mount that is very flimsy and not very strong, and I don't recommend those. Dobsonians are great, but if you have to, Celestron makes good telescopes. You can get like a 130 EQ power seeker, even Celestron First Scope. You shouldn't have to spend more than a couple $100 to get a telescope. Old Meads are fine as well. So start checking out Facebook Marketplace every few days, and you should see a telescope that's going to come up in your price range that you can afford. As well, keep an eye out for binoculars. And you don't need to get the fancier astronomy binoculars. Just regular, say, 10 by 35s, 12 by 35s, 12 by 50s are going to be fine for you to do the start of observing with binoculars. And they just make a huge difference. And just having a pair of binoculars is such a great way to just go through life. They're good for birds and they're good for space. So let me know what you found and maybe your tips and tricks for being able to get astronomy gear relatively inexpensive. Of course, you can go to garage sales, but I think at this point, to find the right piece of gear, you probably want to go on Marketplace. All right, we'll see you next time.